I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solutions of three problems from the section Real Analysis that have appeared from the question paper CSIR National Eligibility Test held in the month of December 2019. These questions are suitable for all these examinations. Right. This is the question bearing the question ID, this one, from part B for 3 marks, and the question is related to limit inferior and limit superior. The given question is, let Xn be a sequence of non-negative real numbers. It's a sequence of non-negative real numbers. Then which of the following is true? We are given 4 options. Option 1, limit inferior of Xn is 0 implies limit of Xn square is 0. Option 2, limit superior of Xn is 0 implies limit of Xn square is 0. Option 3, limit inferior of Xn is 0 implies the sequence Xn is bounded. Option 4, limit inferior of Xn square is greater than 4 implies limit superior of Xn greater than 4. Let's now discuss the solution of the problem in detail. We have Xn, a sequence of non-negative real numbers. Let's take the option 2. Right. Limit superior of Xn is equal to 0. We have to show this implies limit of Xn square is equal to 0. We have the sequence Xn where Xn greater than or equal to 0 for all n belongs to n. We are given limit superior of Xn is equal to 0. It is known limit inferior of Xn is less than or equal to limit superior of Xn. This will imply limit inferior of Xn is less than or equal to limit superior of Xn is 0. That is, limit inferior of Xn is less than or equal to 0. Limit inferior of Xn cannot be less than 0 since the Xn is as the sequence of non-negative real numbers. Therefore, limit inferior of Xn is equal to 0. Thus, we got limit superior of Xn is equal to limit inferior of Xn is equal to 0. This implies the sequence Xn converges to 0. That is, limit Xn is 0. When limit Xn is 0, limit of Xn square is also equal to 0. Agreed. So that means the statement that is given in option 2 is true. Option 2 is true, and it is from the section B, only one correct answer will be there. Therefore, that is our answer. The answer to this question is option 2. That is the detailed discussion of the solution of the given problem. Right. We move to disprove the other options. Option 1, limit inferior Xn is 0 implies limit Xn square is equal to 0. Option 3, limit inferior of Xn is equal to 0 implies the sequence Xn is bounded. Right. We give a counter example. Consider the sequence Xn where Xn is 0 when n is odd and Xn is n when n is even. That is, the sequence is 0, 2, 0, 4, 0, 6, etc. Let S be the set of all limit points of this sequence. It's clear. The set of all limit points, it has only one limit point, that is 0. Therefore, limit inferior of xn is equal to the smallest limit point of the sequence. There is only one, and that is 0. Smallest is 0. So, limit inferior of xn is 0 we got as in the hypothesis. Now, consider the sequence xn square. So, that will be 0, 2 square 4, 0, 4 square 0, 16, 0, 6 square 36, etc. Clearly, this sequence xn square is divergent because the even terms, when it is squared, they are becoming larger and larger. Right, it is xn square is divergent. Therefore, limit xn square is not 0. Is not 0. So, thus the sequence xn has infimum of xn is 0, but limit xn square not equal to 0. So, therefore, the option 1 is not true. Coming to the option 3, in the same example, notice that the sequence is not bounded above, because the sequence is becoming 2, 4, 6 in the even positions, etc., becoming larger and larger, and it is not bounded above. So, therefore, it is not bounded. So, the limit inferior of xn is 0, but the sequence xn is not bounded. Thus, option 3 is not true. Summarizing all the options, the answer to this question, there is one more option, option 4. Limit inferior of xn square is greater than 4, implies limit superior of xn is also greater than 4. Right. We consider a counter example. Consider the sequence xn, that is 3, 3, 3, 3, that is a constant sequence. That means xn is 3 for all n. Right. Clearly, limit superior of xn is 3. It's a constant sequence. It's 3. Right. And now the sequence xn square is 9, 9, 9, 9, etc. And clearly, the limit inferior of xn square is 9, which is greater than 4. But limit superior of xn is 3, which is not 4, which is not greater than 4. It is 3, which is not greater than 4. Limit inferior of xn square is greater than 4 does not imply limit superior of xn is greater than 4. Because limit superior of xn is 3. It is not greater than 4. So, option 4 is not true. Now, summarizing all the options, the answer to this question is option 2. Right. That is the detailed discussion of the solution of the given problem. Let's move to the second question. This is the question from part B for 3 marks, bearing the question ID this one. It is related to the concepts of bounded countably infinite sets. Right. Let capital X be a subset, be an infinite countable bounded subset. Infinite countable set means countably infinite set, and it is bounded. Which of the following statements is true? We are given 4 options. Option 1, X cannot be compact. Option 2, X contains an interior point. Option 3, X may be closed. Option 4, the closure of X is countable. We are given X is a countably infinite bounded subset of R. Now, option 1, X cannot be compact. Right. Now, let consider the example. Let Y is equal to 1 by n, n belongs to n. And Y is countable, and it is countably infinite because it is in 1-to-1 correspondence with the set of natural numbers. That is, and it is bounded below by 0, bounded above by 1. So clearly, Y is a countably infinite bounded subset of R. Now, if we adjoin all limit points of y to y, then the resulting set y union y prime, let's call it as x, is closed because it contains all its limit points and bounded in R. So what will happen? We have adjoined y prime. Y prime is the set of all limit points of y, thus resulting a new set x, and that will be closed and it is bounded in R. So what you will get? X is equal to y union the singleton 0, that is the set consisting of 1 by n, n belongs to n, union the singleton 0 is compact. But it is given x cannot be compact. So therefore the option 1 is not true. Let's move to the next option. Option 2. X contains an interior point. Is it so? When it is a countably infinite set, countably infinite sets have no interior points. That is the fact. So we argue we have X a countably infinite bounded subset of R. Right. So assume that X contains an interior point, say A. This implies A belongs to X because interior points are the elements of the set. A belongs to X and A is an interior point of X. When do you say A is an interior point of X? If there exists a neighborhood which is entirely neighborhood of A which is entirely contained in X. This implies there exists a neighborhood of A which is entirely contained in A. This implies there exists a delta greater than 0 such that the neighborhood of A with a radius delta, which is the open interval A minus delta to A plus delta contained in X. But look at A minus delta to A plus delta. It is an open interval. The open interval consists of uncountably many real numbers. Therefore, it's an uncountable set. So, an uncountable set is contained in X. Therefore, X is uncountable, which is a contradiction to the fact that X is a countably infinite set. So, X is uncountable because the open interval A minus delta to A plus delta is uncountable. Right. We arrive at a contradiction. So, our assumption is not true. Therefore, thus X has no interior points. So, option 2 is not true. It says X contains an interior point. It doesn't. So, option 2 is not true. Move to the next option. Option 3. X may be closed. X may be closed. Now, we have X a countably infinite bounded subset of R, and if X contains all its limit points, then X is closed. Yes, it can be closed provided it contains all its limit points. Therefore, X may be closed. What is the example? That X may be closed. X is equal to 1 by n, n belongs to n, union the singleton 0. It may be closed. So when X is a countably infinite bounded subset of R, it may be closed when it contains all its limit points. For example, this one. So there's option 3 is true. Right. We move on to the next option. Option 4. Closure of X is a countable set. We have X a countably infinite bounded subset of R. Right. Consider its closure. Closure of X is countable. It is given. It means closure of X means X bar. X bar is equal to X union X prime, where X prime is the set of all limit points of X. So X bar is countable means X union X prime is countable. But X is a countably infinite set, and X union X prime is countable will imply X prime is countable because the countable union of countable sets is countable. So we have to look for an example. X a countably infinite bounded subset of R, but the set of all limit points is not countable. So consider X is equal to open interval 0 to 1 intersection Q, the set of rational numbers. That means we are considering all rational numbers in the interval 0 to 1. They are countable because the set of rational numbers is countable. Right. It is an infinite set also. Right. And it is bounded. It is bounded below by 0, bounded above by 1. So, now that X is the countably infinite set because Q is countably infinite and X is bounded because the open interval 0 to 1 is bounded. Agreed. Agreed. Now X prime. So if you take X prime, that means the set of all limit points of that one, all real numbers that lie between 0 and 1, including 0 and 1. That means the closed interval 0 to 1. And it is uncountable. And it is uncountable. So therefore, the closure of X is not countable when X is the open interval 0 to 1 intersection Q. So the option 4 is not true. Summarizing all the options, the answer to this question is option 3. That is the detailed discussion of the solution of this problem. Move to the next question. This question is from part C for 4.75 marks with this question ID, and it is related to the concepts of alternating series. The given series is, let n be a fixed natural number, then the series sigma m greater than or equal to n minus 1 to the power of m by m is, we are given 4 options. Option 1, absolutely convergent. Option 2, divergent. Option 3, absolutely convergent if n greater than 100. Option 4, convergent. Let's now discuss the solution of the problem in detail. We are given n, a fixed natural number. N is a natural number and fix it. Fix it. Right. We have the series sigma m greater than or equal to n minus 1 to the power of m by m. That means the first n minus 1 terms are not included in the series. And the series starts from the term, nth term onwards. Now, that means you recall a result by adding or removing a finite number of terms at the beginning of an infinite series does not change the convergence or divergence of the series. That means the convergence or divergence of the series is not altered by adding or removing a finite number of terms at the beginning of the infinite series. So in this case, the first n minus 1 terms are removed. So without loss of generality, we talk about the series m greater than or equal to 1 minus 1 to the power of m and discuss the convergence and divergence. Right. Right. We consider option 1 says that the given series is absolutely convergent. Option 3, absolutely convergent if n greater than 100. Right. Now what do you mean by absolute convergence? Take the series with their absolute values. So, in our case, sigma m greater than or equal to 1, absolute values, absolute value of minus 1 to the power of m by m. Minus 1 to the power of m, absolute values plus 1. Sigma m greater than or equal to 1, 1 by m. What is this series? This series is divergent by P series test. Recall the P series test. The series sigma 1 by n to the power of p is convergent when p greater than 1 and diverges when 0 less than p less than or equal to 1. In our case, 1 by m, the power is 1, that is p is equal to 1, therefore it is divergent. It is well known that this series is divergent by p test. Right. So therefore this series sigma m greater than or equal to 1 minus 1 to the power of m by m is not absolutely convergent. Therefore, by deleting the first n minus 1 terms also, it is not absolutely convergent. So thus sigma m greater than or equal to n minus 1 to the power of m by m is also not absolutely convergent. Thus option 1 is not true. What about option 3? Now in this case, when n greater than 100, n is fixed. Whatever number you take greater than 100, it is fixed. And you are removing all those terms. Even then, given n is fixed natural number, let n be greater than 100. So n is fixed, n greater than 100, some number, it is fixed. Now, we are talking about convergence, absolute convergence. What is absolute convergence? It is the convergence of the series with absolute values of the terms. Therefore, sigma m greater than or equal to n minus 1 to the power of m by m is not absolute convergent even when n greater than 100. Right. Thus, option 3 is also not true. We move to the next slide. Option 2, it is divergent. Option 4, convergent. So we have the series sigma m greater than or equal to 1 minus 1 to the power of m by m. And it is an alternating series. Minus 1 to the power of m is appearing there, therefore it's an alternating series. When it is an alternating series and am, this is minus 1 to the power of, this is minus 1 to the power of m into am. I'm sorry. Am is 1 by m. Let's recall Leibniz test. It is a Leibniz test for alternating series. We have the alternating series sigma minus 1 to the power of n plus 1 into an, where an greater than or equal to 0 for all n belongs to n. They are all, each an is non-negative real number. And that alternating series is convergent if the following conditions are satisfied. Condition 1, limit n tends to infinity of the nth term is 0. And second condition, the sequence an is monotonically decreasing sequence, that is an plus 1 less than or equal to an for all n belongs to n. Let's come down to our question. The condition 1, limit m tends to infinity of am is limit m tends to infinity of 1 by m is obviously 0. First condition is satisfied. Now, second, for all m belongs to n, we have m less than m plus 1. Yes. 1 by m plus 1, this will imply 1 by m plus 1 is less than 1 by m. Yes. That is am plus 1 less than or equal to am. They are strictly decreasing for all m belongs to n. So, it is a monotonically decreasing sequence. So, both the conditions of the Leibniz test is satisfied. Therefore, by Leibniz test, for alternating series, the given alternating series, sigma m greater than or equal to 1 minus 1 to the power of m by m is convergent. Therefore, the given series, sigma m greater than or equal to n minus 1 to the power of m by m is also convergent. And option 2, that it is divergent, is false. So, thus option 2 is not true. Option 4 is true. Summarizing all the options, the answer to this question is option 4. That is the detailed discussion of the solution of this problem. Right. And all these problems, these 3 problems, are looking to be very, very simple. I am sure that you can do it comfortably in any examination. Right. I am sure that you have understood the solution of this problem Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Let's hope to meet you once again in another episode of Learning. Enjoy learning mathematics. I wish you all the best. Thank you.